Good morning. So I'll talk about magic triangle of CFTs. And this work, which will appear soon, is done with Kai and Son of University of Science and Technology of China at Hefei. And I have some related work done previously with him and Hua Wang, who is in Wuhan University. So motivation comes from various directions. One is classification of 2D rational conformal field theories. And what rational conformal field theory means, among the 2D conformal field theories, you have finite number of primary operators, which leads to central charge and conformal weight to be rational number. Now, one of early breakthroughs was done in 1988 by Masato Muki and Sen, where they just want to look at the case where this 2D conformal field theory is made of the vacuum and then single primary operator with some disanalysis. In that case, they find these characters, torus partition function, satisfy modular linear differential equations, and then by studying the solution of this equation numerically, they find a list of them, which I'll show you later. And also, they're having various attempts to find this one, especially modular tensor categories, and again, these modular linear differential equations, Hecke transformations of some finite group representation analysis, and so on. So people are expanding our knowledge of this 2D rational conformal field theories. And one of these series discovered by Masato Muki and Sen is basically Fest-Jumino-Witten model related to exceptional groups. And that series of exceptional groups, including G2, F4, E6, E7, E8, is called the Delin-Svitanovich series of exceptional Lie groups. And Svitanovich, who was particle physicist turned to statistical physics, he started to study this series from 70s. So that's why their name is there, even though they are like 10 years later. And Delin, mathematician, came 90s. And somehow whole series, his name is attached, not Svitanovich or this guy, but Delin occupied the name of the whole this series. So most of mathematicians call it as a Delin series. Now, somewhat related, but somewhat different angle is division algebra, which is, which again I'll review briefly, which is made of real number, complex number, quaternions, and octonions. And they play the role in supersymmetry, supergravity, and superstring theories. And also recently some work done related to moduli space of 3D supergravity and magic squares. And all these things are coming together in this talk. So outline is first I'll review briefly 2D conformal field theories, characters, and these modular linear differential equations satisfy characters. And then I'll relate some of it to 3D n equal 4 ranked conformal field theories, and also 4D n equal 2 superconformal field theories, about which I'll very briefly mention that. And then I'll introduce magic squares, triangles, and related to the rational conformal field theories. And then I'll give a certain structure about Fest-Jumino-Witten model on this magic triangle. And then I'll list not only we find these 30 theories on magic triangle related to 30 generalized or Lie algebras, and 17 of them are standard Lie algebras, and then 13 of them have uncertain nature. And then turns out they have additional magic structures, which we found very interesting. And then I'll mention higher level theories and then conclude with some remarks. So, so let's have a very brief review of 2D conformal field theory, characters on torus, and then equations satisfied by them. So as I said before, 2D rational conformal field theory is a theory with a finite number of chiral primaries and characterized by central charge and the conformal weight of these primary operators. And we are just looking at holomorphic part of it. And characters are torus partition function of the Hilbert space for each primary operators and their conformal descendant, and they have this vector-valued modular forms given in terms of this fractional power minus C over 24 plus HI, and then Ri is the representation of this operator under the whatever chiral algebras. And then these characters satisfy modular linear differential equation, which was suggested, explored for Ising model by Eguchi and Oguri. And Matsuo Muki-sen took over and then used as the main tool to classify the 2D conformal field theories, especially rational ones. And as I said, these characters are weight zero vector-valued modular forms. And with this famous Ramanujan-Serret derivative, which is like a covariant derivative on modular forms, if you apply this derivative on these modular forms, then you get again modular form of weight twice bigger than original modular form, and R is the modular weight of this. And then they satisfy these nice differential equations. So when once you know the theory, then you can find the equations. But once you have equation, then you can find the theory by looking at the appropriate solutions. So as this MMS, if you start two characters, vacuum and the single characters, and then modular under the modular transformation, which is SL2G transformation, this invariant partition function and M characterize how many degeneracy it has for this non-trivial primary operators. So characters are given by that, and equation satisfied by these two characters second order. And again, this equation is written by MMS, Matsuo, Muki, and Sen, 88. Then Kaneko Jagier came 10 years later and grabbed the name. Again, I don't know why. So for given central charge, there's enough structure in there so that H is given in terms of central charge. And then this coefficient is again given in terms of H, but this form is prettier than written in terms of central charge. And also, amazingly, I guess, dimension of, if we think of a best Jumno model, then the central charge is given in this standard form, level times the dimension of group divided by level plus the Dior-Coxeton number. And I think I missed the expression where Dior-Coxeton number is given again in terms of H, so that once you have this equation, then equation forces everything to be structured, so that once for given mu expressed in terms of H, then C is fixed and mu is fixed and the central charge is fixed because Dior-Coxeton number is fixed and dimension is fixed and so on. So this theory is enough structures to narrow down to very short list. And that's the list Matsuo Muki Sam found, where we have well, central charge, and then I don't think they bothered to write down Dior-Coxeton number, but they identified that this one is EFS Jumno model, E7, E6, F4, D4, SOH, G2, SU3, SU2, and the Liang models. And then they found one more theory, which was 10 years later, or more than 10 years later, identified as not the standard Lie groups, but some intermediate Lie algebra, which is living between E7 and E8. So this series discovered as Svetlanovic and Delin, 70s and 90s, is this exceptional Lie groups, G2 is, there's F4, which is again missing. E6, E7, E8, and then this MMS discovered there are two more. One is Liang, and then there's E7 and F. And not only that, Delin discovered that for this series of Lie groups, dimension is given in terms of Dior-Coxeton number, and then higher dimensional representation made of ordinary representation, especially theta is the highest root, and the twice highest root is like you get from the symmetric product of this ordinary representation, and dimension is again given in terms of closed form in terms of Dior-Coxeton number. So one can give a uniform treatment on exceptional Lie groups. And Cohen-Demand discovers 25 such formulas. And then Landsberg-Manuel discovered for arbitrary higher this root in terms of these dual-Cox numbers. Yeah. Yeah. All 25 minutes. Yeah, and we discovered a few more, but anyway, that's just for the representation build up from the ordinary representations. For fundamental representations, there are more involved story, and I know a few people have been studying it, but I don't see any published materials. And then also, Matsuo, Muki, Sen discovered this beautiful causal relation. So we know that E8 can be split into S2 cross E7, S3 cross E6, G2 cross F4, D4 times D4, and also you can split into Liang theory plus, and the sum of they put notation A1/2, and then E7, and I can tell you more about half, but E7 plus half. Now, causal relation tells us that these series, so you can fold this, so as a conformal field theory, you can combine the conformal field theory of this guy and conformal field theory of this guy to produce conformal field theory of E8. And E8 case, there's only one primary operator, which is vacuum primary operator, and this character is given in terms of Klein J function to the 1/3. And turns out that this can be split into, say, characters, vacuum character of this guy times vacuum character of this guy, plus Diderot's times non-trivial primary operator characters of each one of them. Then this is a very beautiful relation they have discovered. So A3D5, they don't belong to this class. So again, of course, you can do it, but you need more characters. A3D5? Yeah, right. So you need more characters. So it will be different kind of structures. Now, so this series has been appeared many times, but more recently, there are work done by various people related to 3D n=4 rank 0 conformal field series and 4D n=2 superconformal field series. And these theories have a certain relation to Delin Svetanovich series VOA. So Dongmin and has been pioneering, Dongmin Kang in Korea has been pioneering, and he gave a talk in string math here. And basically, you start with 3D n=2 3 gauge series, and then somehow you RG flow to IR, then you end up with 3D n=4 rank 0 conformal field series, which means it has no Coulomb phase or Higgs phase. And then this theory one can relate to non-unitary 3D 2D theories as a boundary hierarchy algebras, and among which you get the simplest, smallest theory with the lowest central charge is related to Liang theory. So that's a beautiful result. And then they generate many other cases. And also more recently, from the 2019 to 24, 25, I guess we just heard a talk from Radamat. Again, Delin series appears, and then they are related to 4D n=2 superconformal field theories and showing that series in various ways. So again, we are interested in what is there in 2D and how it's talking with 3D and 4D physics. So related to that, there are something, this Delin series, and there is something else which is called the magic square and triangles. And then we are generalizing this Delin series to triangles. So this magic square starts from study of division algebras, which we heard of from our high school days and college days, where there are division algebras are like real numbers, so we can add, we can multiply. There's identity, 0 we can add, and there's inverse. That's why we can divide it. That's why it's division algebra. and one can give a norm, which is non-negative. And this normed division algebra over R is possible only for p equal to 2, 3, 4, 8. And 1 and 2 is real and complex numbers. They are associative and commutative. And 4 is this famous Hamilton's quaternions, which is associative but non-commutative. And octonions are non-commutative, non-associative, and this is an 8-dimensional object. And last 20 years, it has been discovered several times. There are something called the sextonion, which is not division algebra, but which arrives from octonions, especially there is called the split octonion, which means 8 plus sign and 8 minus sign. So a very Lorentzian space where you can go to some Lycon and some null directions. Then you can have some object which is living on the sixth dimension, which is called sextonion. And one could imagine quaternions, trinium coming from the null direction of split quaternions, but this seems to be less developed. So that's the division algebra. Then for some reason, mathematicians study, there are many directions, projective planes made of this pair of the division algebras. And then especially if we think about, say, projective plane, say P2, then with RP2, which has symmetry SO3, and that's the A1, SV2. And it's for complex numbers, CP2 symmetry group is SV3, which is A2. And quaternions, we are not sure about HP2 symmetry group is C3, or C3 is SP3 or USP6. And then octonion projective space has a global symmetry F4 and so on. So now, instead of real number, if you think about something else, higher one, then you need some additional mathematical tool, which is called incident geometry. And with that, this geometry has symmetry groups discovered by Prudential, Titz, and Weinberg in that very nice square forms. And you can see this E8 is living at the octonion, and this part of the Helene series appears. So F4, E6, E7, E8, and I missed the F4 in my previous transparencies. Now, Sviatonovich and discovered, because he discovered also Helene series, Helene series, he wants to fill the triangle, so that's the triangle he appears in final. He had a preprint, but then final version of the book appears in 2009, and that's his table. And he put as if it's like a periodic table, and then give various dimensions and the fundamental representation is like atoms. And then Helene gross also extended with different motivations, and that's magic square, and then that's the triangle they had. But both of them missing E7.5 and Liang. And you wonder what is the more extended version of this magic triangle. And so that's where we are coming in. And to do that, we again study this the result, I guess. So we complete the magic triangle. And so we have E7 part. And then we have this one more columns. And then end point, there's a Liang theory, then we filled all the gaps. And then, this theory is invariant on the reflections, and the coordinate given in terms of A, which is Landsberg manual variable, is like dimension of the octonion A6. Sextonion is related to E7.5, and then 4, 2, 1, 0 real numbers, and so on. But the Helene gross parameter is called, this reparameterization gives 1/5 to 5. And funny thing is, Radamat used this parameter in his table. I forgot to tell him that this parameter is known previously. Right, so this theory, there are 30 of them, because this is reflection invariant. And we want to give so out of 30 theories, 17 of them are standard Lie groups, and 13 of them are non-standard. It's not Lie algebras, or it's called intermediate Lie algebra, or some of them doesn't even have that structure. We are not sure about the structures of the series, but as a physicist, we can work on the series. And if we have a Lie algebra, we can have a basis germinating chiral algebra, which is very standard thing. So for Lie algebra, we have dimension, zero constant number, then we can write down to the rational conformal field series of level k with a natural number k. And central charge is given in terms of these formulas, and primary operators for each representation whose inner product is this highest root is smaller than k, and then conformal wave for each representation is given in these formulas. So that's quite standard. So we can find the theories, and we define as a theory mu nu k is equal to theory mu k, extended mu and nu, sorry, for typo. And as this series of Lie groups name has been known, so that's a Switzerland-Dellin series, and this we call the intermediate series, and we study the rational conformability along this one, and X exceptional series, several series, and several section series. This is all mathematical and words, but they haven't studied conformability. No, they didn't look at this corner bit and also this intermediate Lie algebra related to sextonians. A half theory is it has any level which is known. Right, which has right. Those are part of the minimal series. Yeah. A7.5, you can go to level 5, and then something breaks down beyond the level 5. Yeah. Right. Of course, Severin didn't know about M2. He knows, and he doesn't know about these levels because sometimes physics gives a finer structure than what mathematicians have known about. M2 is made of the T2A and this guy and this central charge 2 strange object, which unfortunately I didn't put into my slide, but it's known before from different contexts. Right. So T2A is related to monster groups and so on. So this is a tri-state pub model, and this is a product of the Ising and the tri-critical Ising. So M2 is a combination of these two. This is central charge 4 5, and this is 6 over 5. Together is a central charge 2 theory. So I'm looking for this maybe related to Hegel, but I haven't heard, because Hegel everybody is looking for, and the M2 is the most possibility because it is made of also tri-state pub model, which is related to Hegel. So, well, thank you for reminding me. Right, so this 30 theories, 17 standard Lie algebra, 13 intermediate general Lie algebras, and we are trying to construct these theories. Of course, we can go through phase generator models for standard case, and we can build up, but that's not the way we want to approach it. And somehow we find something very nice structures. So something similar to Dellin series, where dimension of the Lie group is given in terms of Joule-Coxeter number. Now we can write down uniform formula of dimension and Joule-Coxeter number in terms of this coordinate mu and nu, which has this mu and nu. So once you have two values, then you can pinpoint a series. then we can write down the central related level 1 case, central charge and zero constant number. Oh, so I'll tell you something about it. So, right. So we gave an independent study along these directions, and some of them has only level 1. You cannot go to level 2, which is a bit strange. And these two guys have a dimension 0 and zero constant number -1. So level 1 is okay, 0 divided by 0. But level 2 is trivial. On the other hand, this guy, made of these two guys, can be going to the higher levels, and so on, so to arbitrary levels. So that's again very interesting. So there's additional structures we don't know about. Right. So so we can give a uniform formula for the dimension of the groups and zero constant number. So level 1 we can write down central charges. And also we find a uniform formula for weight of the component primary operators given in this form. And then one can build a Hilbert space out of the primary operators component descendant. Now, characters can be written in generic forms, and there are 4 independent characters. And vacuum character study is always 1 because we have unique vacuum. Then coefficient of Q studies dimension of the group, and so on. And the other characters has a dimension of representation plus additional things. And this exponent, which is made of the minus C over 24 plus HR, it has this explicit form. And then they have a very interesting structure that alpha 0 plus alpha 1 sum is equal to 0. And alpha 2 plus alpha 3 equal to 1, which will have some medical relation. This implies some medical relations. And then there's 2 kinds of symmetries. One is exchange of mu and nu. Another one is inverting mu to 1 over mu and nu to 1 over nu. And under this transformation, this important parameters transform this way. Now, modular invariant partition function is now we have 4 characters. And there could be some degeneracy, so we made the vacuum is unique, so we'll have these structures. Right, 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 yeah, right, of course. And so I think 17 of them are standard phase stimulated matter, so you know. Oh, 7.5. So there's some controversy, and that's what I want to discuss with you about, is whether there's a VOAs or conformal field theory related to it. And one of the concern is Liang theory also, C equal to minus 22 over 5. But there's effective Liang theory where you exchange the vacuum and the primary operators. Right, but so sometimes I'm imagining 2 conformal field theories, even non-unitary ones, so combined together into E8 conformal field theory. So in that case, correlation functions, if you overlap them, then you will get the same correlation function and so on. So there's additional structure people are talking about, haven't explored. So E7.5 is one of the great challenges. And yeah, that's very interesting question. So they satisfy this without poles, that's what it means, L equals 0. This is 4th order linear differential equations. And the coefficient, because it's weight, say, 4 derivatives, weight 8. Weight 4, then you need weight 4 coefficient, which is E Eisenstein series, and it's weight 2, so to be weight 8 is E6, and so on. So there are 3 unknown parameters, and which can be again fixed uniformly in terms of this mu and u, and that's invariant under these 2 symmetry transformations. Right. So especially nu equal to 5, this series has only 2 characters. And from the, say, nu equal to 5 perspective, only surviving characters H0 and H2, and the rest of them disappears. It turns out if you solve the second order, fourth order equations, then these series, remaining two series, the chi0 and the chi3, have a series which denominator is constantly increasing. So you cannot make it standard modular form, which means integer coefficient. Instead, its denominator is increased. But turns out it has additional structures, which I don't have time to talk about, but it changes the modular form beautifully after making a two derivative and so on. So usually in math literature, with my ignorance, looks like they don't care about some Q series whose denominator is increasing, even though it could be modular. It's not modular form because it's not integer, but it looks like there are additional structures, and we are discovering that additional structures through this study of differential equations. But anyway, so in this case, the modular linear differential equation, quartic equation, factorized into quadratic equation times that. So because two equations satisfy this Kaneko-Jaeger equation. So you two characters are selected. Now, in a case, there is a single character. So again, this guy is factorized for mu equal to 5 into first order equation, and which I was always playing with it, but only recently I realized it has also additional beautiful structures. So magic structures. So we have in principle all the characters and so on. But turns out these characters have additional structures which we didn't anticipate. So degeneracy of chi1, chi2, and chi3, all of them has this nice structure. Product of degeneracy of third character and fourth character is related to the product of this first character, precise vacuum, so second character. And also, this character satisfy this very nice quadratic relation. So product of vacuum character times characters of first chi1 minus these two characters is equal to just a constant, which is the representation of this guy, and from which one can see that relation between representations is that R2 dimension of this chi2 and chi3 product divided by R1 is given in terms of mu and nu. And also from relation, one can see this to say that one can give a parity sign change, and one can give this one to be even and this to be odd, chi1, chi2 to be odd, then this is invariant. I mean, there's no reason. We could just give this one to be odd, but we don't want to change the vacuum. Then chi1 has to be even also. And then this parity, even and odd primary operators seem to be, again, appearing in constant in next relations. So magic quadratic relation implies a lot more than what's appearing here, because when we are writing a characters, all these things, again, can be decomposed in terms of irreducible representation of corresponding Lie algebras. So it's imposing on various relations among the representations, which is very uniform and inside this magic triangle. So one more relation is a magic causal relation. So we are generalizing Marx and Bucchi sense this pairing to the all other cases. So in these cases, as I said before, you combine these two theories to make a E8, and then their characters satisfy these relations. And we are generalizing to any two theories in the magic triangle. So if I have two theories, mu rho and theory nu rho with rho same rho and mu is bigger than mu, then this combination can be written in terms of another theory, which is mu and one of the nu's. So it's like because it's at denominator, mu becomes 1 over nu. And that led to relation between characters with parameters to be decided, and x there is equal to 1, and that's the relation we get. And this relation, again, respects the parity. And that led to, again, the constraints on the representations between theories. So that's the relation between leading dimensions of groups and dimension of representations. And also, especially specific case, if I have a Deligne series, spectrum which is Deligne series divided by intermediate series for given, then we get for any pair, we have to look at it carefully, then you get a single quotient and so on. So this structure tells us that this series appearing at the diagonal component is some sort of elementary object. And so this quotient, magic quotient, which implies an elementary object, but before that, let's look at G2. G2 is made of this triangle, and F4 is made of this triangle, and if we multiply, then all these things, whole triangle is bigger, and it becomes Yale. So that's one of magic constants. And if I start with this C3.5 and then D4, then you can see D2A appears twice. So we have to divide by D2A, then endpoint E7.5, and so on. So this magic constant relation is quite interesting. And that led to there is atoms of this magic triangle. So turns out all these series on the 30 series can be built from the 5 series along the diagonal lines. So this 5 series, this effective Liam theory of central charge 2 over 5, and this 5-3, effective Liam theory, not Liam theory, effective theory with central charge 3 over 5, and then the U1 theory with central charge 1, and then this is tri-state palm model, and this theory is product of the Ising model and the tri-critical Ising model. And interestingly, if you look at the dimensions of this series, it's 1, and these two series have 0 dimensions. Zero constant number is 3 over 2, 2 over 3 is 0, because we know U1 theory has a zero constant number 0, and then this one is -1 and -1. Central charge is given in terms of standard formula, and this is coming from 0 divided by zeros, but they have different central charge, 4 over 5 and 6 over 5. And when you combine these two atoms, it becomes a 2A theory, and M2, and this one is central charge 2. And those are the conformal weights appearing besides vacuum characters. And factor 2, 3 indicates the degeneracy of these primary operators. So one can go to higher levels. And level 2, when for 2 cases, dimension is 0 and the zero constant number is -1. So if you lose the formula, you cannot have a higher level because the central charge becomes 0, because 2 minus 1 and the dimension is then 0 divided by 1 is equal to 0. And so, but other cases, we can find the higher levels. And especially sub-exceptional series is the one where, let's look at the super lineage. Right. Oh. Right, so there could be supersymmetric or super algebra generalization of this magic triangle, of course. That's also very, right. Oh, right, so I was thinking maybe there is logo CFT. And also if I look at the Ramadas talk, then which is theory he talked about where next to Liang theory, where parameter nu becomes 1/5, and that's C equals 0 theory. Instead, he put Liang theory central charge -22/5, not effective Liang theory. And I don't know how, I mean, his index formula, he implies that's the right ones, but this formula gives 0. So I'm very curious whether this formula is wrong or there's additional hidden structure which I'm not aware of. And there's all these stories richer than what we have discovered so far and so on. So, right, so let me see. Right, so that's one thing. And then, let's see, level 2. So it turns out sub-exceptional series comes from the, okay, so Svetanovic series, the intermediate series, then sub-exceptional series. So third one where you end up with E7. And if you go to level 2, then they're all supersymmetric. And there are 11 characters which you can put into 4 NS character and 5 R characters. And then those are conformal weights, and we can write down linear differential equation for characters. But in general, structure is more complicated. So as I said, these two atoms, there's no obvious higher levels, but there could be. But this Liang theory 5.2 and this 5.3 and the U1 level 3, they can have arbitrary levels. And also we made this sub-exceptional series that we said that they have supersymmetries and that they are central charge and the conformal weights and so on. And also, even though there is no universal causal relation, so we also find a very interesting relation between, say, Tallinn series level 2 and the sub-exceptional series and A1 level 2, and they have this minimal model, philosophical minimal model with n depending on the what kind of value we put it in A here, and so on. So we find some new causal relations which has been known. And higher level we study a little bit more, but one can make some general statement about it, but nothing really deep or except that previous study of this intermediate series, exceptional series led to some cases you cannot go higher level, like level 3 and so on. So let me conclude. So we identified all the theories in the magic triangle, and we worked out rank 1 and some of rank 2 characters. And we find the magic quadratic and the causal relations and 5 atoms or elementary particles of these theories. And then some exceptional series at level 2 has n equal 1 supersymmetries. And further implications are expected in representation theories are expected. And I hope some of these Tallinn series appeared in for the 2D correspondence, and we hope that rest of series in magic triangle also appears in these relations. So thank you for your participation, and have a safe journey home. I'm the one of the hosts. Thank you.
Any questions?
So actually, I have two, but so one of them is: do you expect to have a magic pyramid if you look at theories with 6 characters instead of 4? Because for 2 characters you have the series, and then for 4 characters you have the triangle.
Yeah, that's quick generalization, but I heard, again, my lack of mathematics, and I was looking at John Baez's papers on Ottonian. So the reason, of course, what is it? Right. That's something very good, because right, who knows, right? So 6 characters, then there'll be one more axis with the same tendencies. So with mu new row, 3 coordinate, and then there could be the whole series. Nothing prevents it from that, right?
So actually, yeah, to my other question, so I think I remember in the Landsberg-Manivel series,
Right.
you can find it by imposing some integrality relation. You have some kind of Diophantine equation that you impose on their formula, and
Right.
then you find immediately all the series.
Uh-huh.
So I was wondering, is with your formulas for the depending on mu and nu,
Right.
can you just by imposing some integrality relation on that formula, can you find all the triangles? Do you know if this?
Oh, of course, we went all the way around because we know this series. Then we put the coordinate and we fix it. But you could say there could be a more structure in there. So this triangle could have a finite structure, so we'll test all there is and so on. If you impose the integrality on central charges or whatever, and then that could be the unique answer. Yeah.
Any other questions? If there are no further questions, then let's thank the speaker.
Thank you.